So we have three goals looking at the regression statistics. The first is to figure out how much of the variation of the asset or portfolio's returns are explained by the factors. Do that looking at the R squared and the adjusted R squared. Then we'll look at whether or not the factor that we chose actually explains returns. Is it a priced factor? We'll look at beta and the p-value, and then we'll look at whether or not there was excess return. Did this portfolio or this asset really beat the market on a risk-adjusted basis? And we'll look at the alpha and the p-value. But let's spend some time looking at these three different statistics in a little bit of depth before we go back to a spreadsheet and look at some actual data. And we'll use our CAPM regression. So this is a single factor regression model. That factor is an index and that factor is the market index. And note that I've dropped the T's, the T's next to the RI and the RM and the E, but note that there are 60 of these, 60 of these, and 60 of these, but only a single alpha and a single beta. And remember, we choose this alpha and beta to minimize the error term. And we'll see this visually in a minute when we go back to the spreadsheet. So here's the idea, is that the total variation in the return of an asset, in the return of asset I, so the total variation of RI is the variance of the return of this asset I, the variance of RI. And we can write that as sigma I squared. This is how we would write that. This is the variance of the return of I. And so I can take my equation, Ri equals alpha plus beta times Rm plus E, and I can say that the total variation is going to be the variance of the left-hand side and therefore the variance of the right-hand side. And then I can distribute. And I can say that the variance of A, the variance of alpha, plus the variance of beta times the return of the market, plus the variance of the error terms is going to equal the total variation. Now this one's a little confusing maybe, but the first step is to realize that this never changes. That alpha is constant, and so the variance of something that never changes is 0, so that drops out of the equation. And what I'm left with is the beta squared times the variance of the market, plus the variance of the error terms. And so therefore the total variation, the variance of the return of this stock, and this is, remember, how it does relative to its mean. Sometimes it's way above its mean, sometimes way it's below its mean. This has two components. The first component is how much the market varies times the relationship between the stock and the market, and the part that's the error terms, the variance of the error terms. So we can break total variation into two parts. The portion of total variation that is explained by the factor, which in this case is the market. For the CAPM, this is also called systematic variance or market variance. And the portion of total variation that is not explained by the market or is unexplained. For the CAPM, this is also called non-market or idiosyncratic risk. And so again, the total variation or the volatility of the stock can be explained by the portion that is due to the market and the portion that is not due to the market. We call this explained and unexplained in the context of our regression. The R squared is telling me the portion of total variation that is explained by the market. And so the R squared is going to be, by definition, we define the R squared this way, as the total variation, the explained variation divided by the total variation. But I already know the total is equal to explained plus unexplained, and so I get this relationship. R squared is explained variation divided by total variation, and total variation is explained plus unexplained, and so I can see that if this is a really, really, really big number, if there's a lot of variation in these error terms, then R squared is low. And if there's not a lot of variation in the error terms, then R squared is high. And so mathematically, R squared is a function of how much variation there is in the error terms. And later what we're going to see is how widely spread the dots are relative to the line. If the dots are really, really, really close to the line, then there's not a lot of unexplained variation. R squared is very high. But if the dots are really, really far from the line, then there is a lot of unexplained variation, and the R-squared is very low. And just to be clear, and I know this is super annoying because up here I have R for return, but now I'm talking about R-squared. This is a different use of the letter R. So this is the regression R-squared. It's not the return R. And so again, R-squared is the explained variation divided by the total. The difference is the variance of the errors, the spread of the dots relative to the line. The wider the spread, the worse the fit, the lower the R-squared. And the tighter the dots, the better the fit, the higher the R-squared, the more variation of the asset or portfolio's return is explained by the factors, which in this case is the market. One more thing, when we have multivariate regressions on the right-hand side. So if I add a new variable to my regression, I can't decrease the explanatory power. It might do nothing, although that's unlikely. Just by random chance, it's going to explain a little bit more of the variation. And so adding new variables can only increase the explanatory power of my model. The adjusted R-squared only increases as we add new variables to the right-hand side if the new terms that we add to the model, the new factors that we add to the model, improve the fit by more than we would expect if it were just random chance. And so the R-squared will get bigger, but the adjusted R-squared only gets bigger if the amount of explanation exceeds what we would expect if it were random. We're not going to have to worry about the adjusted R-squared for now. We will when we move on to multivariate regressions in Chapter 10.